Ladies and gentlemen, the last time we came, we ended with linear programming, the minimization. And this is where we converted the minimizing cost, we converted it into the standard form, which is what you see on your screen. Today we want to look at very strange kinds of linear programming models or approaches. They are strange, and you see how strange they are. Okay, and there are 4 of them. We are going to have different names for each one of them. First one is known as multiple optimal solution or ultimate optimal solution. So as the name implies, the number of solutions you're going to get is not going to be one. In other words, the solution will not be on a point, but it will be on more or less a line. So the solution is a lot on a line. So let's look at that first. Okay. In reality, the objective function will always be parallel to one of the constraints. This is the easiest way to understand multiple optimal solution. The objective function that you have, it will be parallel to one of the constraints. And you guys might remember that usually when you are trying to find the solution, graphical solution, what you do is that you have an isoprofit line. You have a kind of an imaginary isoprofit line, which you create yourself. And we learned how to create it. And what you do is that you shift the isoprofit line upward or downward until the last section, it will be, or the first section, it will be tangent to the one of the corner solutions. So the last of the corner solutions, that is if you are shifting it outward, parallel down, or the first tangency point, if they are shifting it from up coming down, and I'm assuming a minimization. In such a case, for optimal solution, it will be at the corner. For the optimal solution, it's going to be at the corner. However, for multiple optimal solution, it will not be at a corner. For multiple optimal solution, it will be on the line, one of the constraint line. So the isoprofit line will be sitting on one of the constraint lines. And this normally happens when there is a formulation or a statement from different managerial angles. So what we want to do is that we want to draw this line. Look at this very line that you have on your screen. We are going to plot this. And something will happen in the course of the plotting that will give you a clue that there appears to be a problem with this. Now, a way to identify each of these strange, irregular types of linear programming, the best way is by drawing. The other way is by computing. Okay. I will be applying both as times will allow. So we are going to plot what you see on your screen here. And so I'm going to create a board, and then we start the writing. All right. So here you are, and we have an objective function which is z equals to 3x plus 2x2. So the z function is going to be z max, and that is 3x1 plus 2x2. And this is subject to some constraints. And in this question, the first constraint was 6x1 plus 4x2 less or equal to 24. This was the first constraint. We don't need to bother much about it. But the second constraint was not a two-variable case. The second constraint was a one-variable case, which was x1 less or equal to 3. And then, of course, our usual non-negativity constraint is also there. I'm sure you guys are with me. So the first thing we want to do is to draw the non-negativity constraint. That has always been the way to go. Okay, you draw the non-negativity constraint first. How do you do that? This is it. You draw it like that, x1 and then x2. That's a non-negativity constraint. Then you draw your first constraint. In this case, let's take the easier one. x1 is less or equal to 3. So apply the equality sign. That will be x1 equal to 3. x1 is on this axis. Okay. So you identify a portion called 3. Okay, and that is 3. And then that means that you have to have a straight line. And this straight line is x1 equal to 3. Then the second constraint, which is 6, 4, 24. Okay, so if x2 is 0, that's how you normally always do. If x2 is 0, we've been doing this many times. It means that you have 6x1 equal to 24, which means that x1 is what? It's 4. Okay. So x2 is 0, x1 is 4. Now, if x1 is 0, if x1 is 0, then you have 4x2 equal to 24, and that means that x2 is 6. Okay. So you have x1 is 4, and that will be somewhere here. That will be somewhere there. And x2 is 6. So we'll take it up somewhere there. And so we'll join these two lines. Okay. We'll join these two lines nicely, and that will be our second constraint. So this will be x1, which is 4, x2, which is 6. So we've been able to draw our constraint. And ideally, if we were to find our feasible solution, okay, if we were to garner ourselves and get a feasible solution, that feasible solution is going to be the area here, the area to the space that you are seeing me. That area will be our feasible solution area. However, the common area both to them will be this section there. The area common to each one of them is going to be this section. That's a common area. Okay. Now, we now go and draw the objective function. And the objective function is 3x1 plus 2x2. Now, the value here, the value at this section, we don't know. So we take an arbitrary number. And like I always say, the easiest arbitrary number is when you multiply the 2 by the 3 and then get a number. So if we are to multiply the 2 by the 3 carefully, you're going to get 6. And when you have the 6, okay, I don't want to go through all these gimmicks. Okay, let me just do it. If you have the 6, it's going to be 6, 3x1 plus 2x2. So if x1 is 0, if x2 is 0, then x1 is what? 2. And then if x1 is 0, if x2 is 0, x1 is 3. x1 is 2. if x2 is 0, x1 is 2. And if x1 is 0, x2 will be 3. So you're going to have x1 to be 2, which will be somewhere there, and x2 to be 3, which will be somewhere there. Okay. Am I doing the, I think it's the right thing, but then my things are not drawn to scale. Okay. My things are not drawn to scale, but if you have to plot it to be something like that. Okay. But ideally, it will be inside there. Now, the next thing you want to do is to increase the numbers. Okay. And I would like to tell you how you should easily connect without even drawing. And of course, you have to draw. Now, if you have to shift this line, this isoprophet line upward, it is going to eventually sit on this 6 and 4 line. It's going to eventually sit on this line. That's how it's going to be. And the easiest way for you to see that is that you see that the link between the x1 and this constraint, watch it, the link. You see that the link between the two is 2, and the link between this one too is 2. So if you multiply 2 by 3, you get a 6, 2 by that, you get a that. Okay. And that is a clear indication that the two of them have got a connection. And so normally we shift the isoprophet line. So if I were to shift the isoprophet line, eventually it's going to sit on this line. And so the space here, the space there, okay, up to this corner point here, every point there, this isoprophet line will be kind of tangent to it. And every point there is a solution. Every point there is a solution. And that is why we have it as a multiple optimal solution. So this is a typical example of what I just did. So every point, you see that it is seated on the line, and every point there will be a solution. Multiple optimal solution occurs when the isoprophet line is tangent. Any question? It's not clear. So it says from the graph, the isoprophet line is parallel to the constraint. Okay. And as you increase it, eventually the situation will be that it will be seated on the line, it will be parallel. And the simplest way, and of course, it's also called alternate optimal solution. The easiest way to know that this thing is the situation is this. When you now get the values, now let's try to get the values. X1 is 3. So if X1 is 8, let's try to find out the overall value. By the way, this is maximized. It's supposed to be maximized instead of minimized. So if you have the value to X1 to be 3 like that, if X1 is 3, what to be the value of X2? If you substitute the 3 here into the constraint, okay. If X1 is 3, let me just do that here, because if I do it somewhere, some of you might not get it. Okay. So if X1 is equal to 3, then you are going to have 6X1 plus 4X2, okay, equal to or less or equal to 24. So that means that you're going to have X1 to be 3. So you have 6 into bracket 3, okay, 4X2. Okay, less or equal to 24. Okay, and that will be 18. If you take the 18 to the other side, it will be 24 minus 18, which will be 6. Okay, so you have 24 minus 18, which is equal to 6. And so your 4x2 will be equal to 6, and x2 will be equal to 2/3. Okay. Now, if x2 is equal to 2/3, what's something? If you drop that into the formation here, so x1 is 3. So this section here will be 9. Okay, this section will be 9. If you drop the 3 there. And then x2 will be 2/3. Okay, 2/3. That is if my computation is right. No. Hold on. It's 24. It's 24. So you get 4x2. It will be 3/2 rather. Is that it? Okay, 3/2. I just want to be sure. Yes, 6 here. Yes, 3/2. So if it is going to be 3/2, then you multiply that by this. Okay. So that will be 3. If you multiply the 3/2 by that, you're going to have 3. You add a 3 to the 9, okay, and that will give you 12. So it means that the z value at that point will be 12. And that z value I'm talking about is this section. Let me just show you. Okay. I just want to wipe off this. I need to clear this and show you. Okay. That z value, that I'm talking about, that point of that z value is at a point B. This is at a point B. So point B gave us a value of what? 12z. Okay. Let's go to point A. The coordinates of point A are x1 is 0, x2 is 6. X1 is 0, x2 is 6. So drop that here. X1 is 0, x2 is 6. So 2 times 6 will also give you what? 12. So at the point B, we have a z value of what? 12. And at the point A, you will also have a z value of what? 12. This is just double solution, all giving you the same thing. So that is why we say any point between the A and the B will give you a solution. And that is why we have multiple. It's a strange kind of linear programming. Now, sometimes somebody might look at it and say it's not good. Sometimes another person might look at it and say it's good. It's good depending on how you look at it. Okay? Because what it means is that it gives managers the flexibility to decide on which one to select. In other words, managers now are flexible. They can make a decision that let's produce X1, 3 of it, and X2, let's produce, 1.5. Or another group will say, let's produce X1 to be 0 and X2 to be 6. Any point along the line is a flexible way of selecting. And that is how some people would look at it. Okay. So the profit will remain the same. Okay. This kind of multiple optimal solution or alternate optimal solution is often used to choose among alternative options. And there's a technique, a linear programming technique for solving that, which is known as goal programming. Goal programming solves situations of multiple optimal solution. Any question on that? So you just need to know, if I give you a mathematical formula and I tell me whether it is multiple optimal solution or infeasibility or redundancy or anything, you should be able to tell me. Let's go to the next strange one. The next strange one is known as infeasible solution or infeasibility. It's simple. 2 constraints or 3 constraints or 4 constraints, but one of the constraints will conflict with the other constraint. And so there is no solution to the programming problem. There is no solution. And the best way to explain this is that there is no intersection of all the constraints. Some of the constraints will intersect. But it might be that sometimes one constraint is violated. And so why did that constraint come in? Okay. One constraint is violated. And this will happen when a marketing manager, for example, gives a different constraint, which differs from a production manager, or it differs from an inventory manager. And all of them are saying, oh, we need 20 baskets of this instead of 16 baskets of that, 40 gallons of this. All of them are giving conflicting, limitations of the resource. Then you have situations. This is a typical example. Okay? And I'm going to show you one typical example right here. So let me just give you let me give you a board, and then we create a typical example here. And again, you got to deduce it from the mathematical model. So let me give you a model, and the model is Z-max. We have Z-max here. And this Z-max, this is an optimization model, and that's equal to 5x1 equal to 5x1 plus 3x2. We have 5x1 plus 3x2. Then you have several constraints. The first constraint is 4x1 plus 2x2 less or equal to 8. Okay. 4x1 plus 2x2 less or equal to 8. And then you have x1 greater or equal to 4, x2 greater or equal to 6. And then, of course, your non-negativity constraints. Try and solve this. Try and solve this. Well, first thing to do, you draw your non-negativity constraint x1 and then x2. Then you draw your x1 and you have to use an equality sign. X1 will be on the axis here, and the number is 4. Okay, so you identify a point here, call it 4, and then it has to be x1 like that. So this will now be labeled at x1 equal to 4. Then you have another equality one, which is x2. x2. And x2 is given as a value of 6. So let's go to the x2, identify somewhere like 6 here. Okay. So that will be number 6. Again, that will be a horizontal line. Okay. That is x2, which is equal to 6. So already they are meeting at a point, but there's a third constraint. Watch the third constraint. I'm not going to work it. Okay. If x2 is 0, what will be the value of x1? Quickly, you can tell me. If x2 is 0, what is the value of x1 in the third constraint? If x2 is 0, what value is x1? Map. Okay, that's 2. So that's 2. Okay, so x1 will be 2. Okay, so we can identify that somewhere at this point here. Okay, and then call it what? Call it 2. And what if x1 is 0? What is the value of x2? You can tell us that too. If x1 is 0, what will be the value of x1? Sorry, if x1 is 0, what is the value of x2? Steven?
Doc, please, 4.
4, thank you. So you now go to this section and then you call it 4. So now we've been able to identify all of the necessary situations that we need to draw our program. But of course, we need to draw our lines. So at this stage, we can now go to this section and then connect the 2 like that. Connect the 2. Now, there is a problem. Okay, there is a problem. Let me just reconnect the 2 well. There is a problem. And the problem is that you can see that this constraint, okay, and let's give it a name well, it is actually 4x1 plus 2x2 less or equal to 8. Okay. Oh, but then it's an equality sign, so let's just keep it equal to 8. So if you look at that very constraint, you can see that it's not intersecting any other constraint. It's not intersecting any other constraint. That makes it a problem. Because ideally, it can decide that if it's not intersecting any other constraint, and of course, you don't need one line. Because if you have only one line, then again, then you have only one constraint. And if you have one constraint, then it means that you don't have a choice. You just have to stick by the one. You just have to produce 4 units of x2, 2 units of x1, and then we shouldn't have even done a linear program. Okay, so that it means it will make only this space, but then what is happening at the top there indicates that this space is already a useful space, and yet this one is that. Now let's even see why the situation will be the case, because remember, the definition of infeasibility is that there is no solution. There is no solution. And when do we say there is a solution? One, there is a solution if there is no conflicting constraints. There is no conflicting constraint. Let's take an example. First of all, you're already telling me that x1 is 4 at the limit. I mean, the truncated limit of 4, okay? So the minimum is 4. And then you're also telling me that x2 is what? Is 6. So straight away, we have our answers here. We have our answers here for x1 and x2. We have to drop them there. Drop x1 here, which is 4. You have 5 times 4, and that gives you what? That gives you 20. Okay. And then you have x2 to be 6. Drop the 6 here into the z value. 3 times 6, and that gives you 18. And so 20 times 18 will give you what? 38. Perfect. Now, if you tell me that x1 is 4, watch it carefully. And I drop that 4 here. I drop that 4 in the second equation. It must be binding. Okay? It must be binding, or at least it must be feasible. If I drop that here, okay, it must be feasible. So x1, if you drop x1 into the first one, you get what? 16. 4 times 4 is 16. And then if you drop the second one, which is 6, into this one, you get what? 2 times 6, which is 12. So you have 12 plus 16. 12 plus 16 is supposed to be less than or equal to 8. Now 16 plus 12 is already, 28. 28 is not less than or equal to 8. So that constraint is not satisfied. And as long as a constraint is not feasible, it makes the whole scenario wrong. So we have an infeasibility. And this infeasibility, we have to find a way to address it. When the linear programming model, and you will later learn that every linear programming has a primal and a dual version. And when the primal version here is infeasible, the dual is unbounded. And we'll come to that, okay? And we'll look at the complementary slackness theory, because that's going to help us to be able to appreciate these things better. So this is an infeasible solution. It's strange. This is not what we are usually used to. It's a strange form of linear programming. But the clue for you to know that this is infeasible is this. This is a clue. When you have a constraint, the constraint can help you get a z value. But when you drop that constraint value to the other constraint, they do not make the constraint feasible. They do not make it feasible. Let's forget even about binding. They are not within the feasible, situation. And that's a typical example of infeasibility. Any question on this? Any question? So this is a situation that you have. Let's go to a typical example. Oh, did I even show this thing correctly? Let me just quickly show you correctly, because otherwise it might look like. Okay. So this, if you look at the symbol here, if you look at the symbol, it was greater than. It was greater than. So we wanted numbers that are 4 or more. And 4 or more means that we are looking at spaces here. Okay. Spaces above 4. So those are our feasible solution area. Okay. Those are feasible. When you draw it, it becomes even easier. Okay. And of course, 6 is the minimum. So again, we can see that we are looking at spaces above. So anything below, which of course this constraint falls in, is infeasible. It's not within those feasible situation. So in a proper drawing, what we had was this. This was a proper drawing that we had. All right. In most of these situations, you have to draw them, because when you've drawn them, you better understand them. So it's always good to draw them to get a bigger. Okay. Now, the next kind of strange, very strange, irregular type of linear programming is known as unbounded. Now remember, there is a connection between infeasibility and unboundedness. Infeasibility means there is no solution. Multiple optimal solution means there are more than one solutions. Unboundedness means there are finite solutions. So you got to really understand this thing. Okay? So no solution at all, zero solution, okay, will eventually correspond to infinite solution. This is unboundedness. Okay? So in unboundedness, the feasible solution area is not closed. Okay? It's rather open. And if it is open, then we have that situation where anything is possible. A typical example we do. Okay, so if it is open, and then we are shifting the isoprophet line, it will keep shifting because it's not getting anywhere. It will be tangent to the objective to the one of the constraints. So you keep shifting it, and that means that you're going to have a lot of profit, unlimited profit and unlimited cost, which is not real. In real market system, that is not possible. So sometimes the problem will come from a wrong formulation. Let's take a typical example. A typical model that can lead to such a situation. So let's take a very fresh look at a typical example. I'm going to give you a Z-max formulation. This is a Z-max formulation. So suppose I give you a formulation like this. And I tell you that Z is equal to 4x1 subject to some constraints. 4x1 plus 2x2. The first constraint is that x1 is greater or equal to 4. The second constraint is that x2 is less or equal to 2. And then you have your non-negativity constraint. If I should give you this, and I ask you the question, this model, is it exhibiting multiple optimal solution, infeasibility, or unbounded? How would you handle it? Well, the first thing you want to do is to draw it. Because when you draw it, it helps you to be able to appreciate it. If I were to tell you to draw, I'm sure you can all be able to draw it. So try it. Try the drawing and show me. Okay, so this is your non-negativity constraint, x1 and x2. You draw the first constraint, x1 is 4, okay, and that's all we've done here. It's a vertical line. X2 is 2. It's a horizontal line at x2. Okay. And they meet here, but that's not your focus. Remember the symbol. The symbol says that, and I'm going to use a different color for this. The symbol says that x1 is 4 or more. So if x1 is 4 or more, we are talking about area here. Area there, 4 or more. That is x1. Now x2 is what? X2 is 2 or less. So 2 or less is looking at the area there, the area here, the area here. Okay. And so you can see that the area that is common to both, I'm going to shade that. The area that is common to both is supposed to be this one there. So this area here is common to both constraints. And this should be where the feasible solution area is. Now, to be able to get that feasible solution area, normally what you do is that you go to your maximize, the z value, okay, and get a number, an isoprofit line. And this isoprofit line, assume a number. So we're going to just assume a number, say 24. I just want to assume 24. So you get 24 equal to, okay, you get 24 equal to 4x1 plus 2x2. Okay. And so if x2 is 0, then x1 is what? 6. Okay. If x2 is 0, x1 is 6. And if x1 is 0, x2 is 12. x2 is 12. So now we are going to plot x1 is 6, which will be somewhere there. x2 is 12, which will be way somewhere there. Let's just say somewhere there, 12. And then we join the 6 to the 12. Oh, no. x1, let me do it again. I'll interchange them. So x1 is 6, that is somewhere here. x2 is 12, let me just go up there. Then you join the 2. Okay. So that is your isoprofit line. I'm going to shift it parallel until it is inside a feasible solution here. But we are talking about what? We are talking about it being tangent to the feasible solution area. Okay. Now, this point here is not tangency, note that. Because at that point there, part of it is inside the area and part of it is at the vertex. Okay. And so the more you shift it there, it will never have a point of tangency. And as long as you keep shifting to the right, every single section there is possible. And it will keep going till infinity. And this is a point of discussion here. That is a clear indication of unboundedness, a clear indication of unboundedness. Okay. So this is a solution that you see. Unboundedness, you can see that you keep shifting and the z value will move towards infinity. And the reason is because, okay, the way you've constructed the constraint, and again, the constraint will always guide you. The way you construct the constraint, you could see that the feasible solution area was not closed. You can see the openness there. If it had been closed with a line, okay, let's assume that there was a line here that now closes. There was another line, let's say another line, that closes. Then you can say that as this thing keeps shifting, it will get to this point of intersection. There is no line, no other constraint to close it. And that's a typical example of unboundedness. The word unbounded means open. And that leaves us with the last kind of irregular linear program. And that last one, irregular linear program. Kajitan, you have a question?
Yes, sir. Please, I wanted to find out. So you can hear me?
Please go ahead, yes.
I wanted to find out if, for you to get the isoprofit line to get into the feasible area, do we have to keep assuming numbers?
Yes.
Different numbers?
Yes. But normally when you assume the first number, okay, it's easy. Remember, you are drawing. It's easy to guess the line because you don't need so many multiple numbers. What you need is that you should assume the parallel nature of the line. Okay, so if you draw a line and then the first line it is inside the feasible solution area, then your next line must be a bigger number which will take you away from the inside until you get outside. So the moment you get outside, you will know, okay? You will know that if I multiply this by that and that, it should take me to this number. And I gave you a clue about how to get a first one anyway. Okay? Sometimes you look out for the other numbers in the constraint, And if they are quite big, you can take some of those numbers to do. But this is a parallel nature. So as you shift it with your mind, you will know it. This assumption, you will know it with scale. As it's shifted, you get it. If you draw one and it's inside, the next one must be outside. Then the other one must be the tangent. If you draw one and it's rather outside, then the next one must be inside. Or finally, on the tangency. Finish. So the maximum you can ever draw is 3. I mean, you should be able to draw it. If you are very skillful, you don't even need a third one. You can only assume the rest. All right. So let's go to the last one, which is redundancy. Redundancy is not really more or less like that, but it has to do more with a constraint. So a redundancy has to do with a redundant constraint. Something that is redundant is more or less like superfluous. It's unnecessary. It's not needed. Without it, we can move on. It's redundant, repetitive. It causes no major difficulty if you are solving the linear programming. But we need to know why it happens. A typical example of a redundant constraint is that it doesn't affect the feasible solution area. It doesn't. Without that, you will still be able to arrive and know your feasible solution area, and finally will still get your objective function value. You don't need it, but then it's there. Okay. So that's one constraint may be binding or restrictive than another, and thereby will negate its need to be considered. So sometimes you may need one constraint, and then you have another constraint. These two constraints are enough. They are enough for you to be able to arrive at the solution. Let's look at an example of a linear programming that we can identify redundancy. And we will know, okay, this is not something that you have to cry about. You will know. Let me see. One of you have posted, why do we have to find it if we actually don't? If you don't need it, okay. Well, you are a research analyst, you are a management scientist. Somebody has given you a constraint. Okay. Let me give you a typical example. It will help you. You go to the marketing manager. The marketing manager says that you need 2 gallons of milk. All right. You need 2 gallons of milk. And then you need 4 gallons of 4 hours of labor. Well, let me put it there. Okay, one says you need 4 gallons of milk, the other, and then 4 hours of labor. So that's what the marketing manager says. Then you go to the production manager. The production manager says you need 8 gallons of milk and then 8 hours of labor. Now you can see that the 4 are inside the 8. The 4 are inside. So even if you're going to put all of these 2 into the situation, you're going to take the information that each one is saying. The first person statement will be redundant because it is being captured by the second one. Okay. And then another person because remember the constraint must meet each other. So let's say that another person gives a different constraint. And that constraint is way outside and it has nothing it's going to do. A typical example will give you an idea. Okay. So let me give you a typical example. Okay. Michael is saying that from the graph, we drew how different is the conflicting graph from the unbounded graph. Michael, I don't understand your question. So you want to come again. You want to ask a question or ask a statement. If it's a statement, there'll be a full stop. If it's a question, there'll be a question mark. But this very one is not clear. So guys, let me just give you a model, a linear programming model. Okay. And then let's see whether there's any redundancy. So let's write a model where you have Z max, which is equal to 1x1. Of course, I can make it x1 plus 2x2. 1x1 plus 2x2. 1x1 plus 2x2. And then this is subject to certain constraints. The first constraint is that subject to x1 plus 2x2 less or equal to 20. That's the first constraint. The second constraint is 2x1 plus x2, and then you have less or equal to 30. Then you have a third constraint, which is x1 less than 25. x1 less than 25. And finally, you have your non-negativity constraint. So this is it. Now, the best way to capture the idea is to draw it. So once again, you have your x1 and then your x2 graph. You have your x1 and you have your x2 graph. So let's take the first constraint. And normally it's nice to deal with the first constraint, which has no two variables. And that is x1. x1 is 25. So we can plot it far end here, 25. Okay, x1. It's a straight one. Then the other one, you have to assume if x2 is 0, if this x2 is 0, then x1 is what? 20. 20 will be below 25. So you bring it down here. Okay. So we can now identify our 20. Then if x1 is 0, x2 will be what? 10. So you can now get some 10 down somewhere here. So you can have your 10. And then these two lines, we can join them and have that first constraint here. Second constraint, if x2 is 0, x1 will be 15. Okay. 15 will be above this. So you can write that there. And then if x1 is rather 0, x2 will be 30. Oh, let me put it up. If x2 is 0, sorry, x2 is 0, x1 will be 15. 15 will be below this. Let me see. If, oh, the first one, I need to just go back and just edit it. Okay, this first one. This first one, it's supposed to be 30. So if x1 is 0, then x2 is 30. Okay, let me just take it. And normally 30 is supposed to be go way up here. Way up here. So let me just assume that it's somewhere up there. Call it 30. And then the second one is if x2 is 0, x1 is 15, which is this one there. So now let's join this 30 and then this 15. So these are the two. And of course, without question, you will notice that the feasible solution area that we want is this area there. Okay. That's the feasible solution area. Now, if you want to find the feasible solution area, okay, you see, we indicated clearly that feasible solution area is these two. The reason is because, and you can see that the first constraint, 25, is redundant. This 25, I don't need it. Okay, I don't need it. Okay, because it captures everything. So to be able to identify the feasible solution area, the common area to all of these constraints, this whole section here is not common. Okay, and so without this, if I should clear this constraint out of the whole thing, I will still be able to identify my feasible. I don't need x equal to 25 to be able to arrive at. So 25, x1 equal to 25 is a redundant constraint. A redundant constraint. Now, a redundant constraint here means that it is not necessary. It has no effect on the feasible solution area from the first two, which are very binding constraints. And that is basically how you got to tackle. So if I give you anything, the best way to draw it, the best way to understand how it works is to draw the constraint and make sense out of the drawn constraint, and then you can be able to now. So what I drew, this is it. This is a feasible solution area, and that x1 is x1 equals to 25. All of that, its region is a redundant constraint. Very good. Any question on this? Any question on this? So if you look at this, the value of the objective function is rising indefinitely. And this is unboundedness, because unboundedness means that it's not closed, and so a lot of things are going on. Now, if you go to infeasibility, infeasibility is not a matter of the value of the objective function is rising infinitely. No, we can get it, but the thing is that it's a constraint. Infeasibility has to do with a constraint. When you put the optimal solution, the so-called optimal solution, into one of the constraints, that constraint is no longer feasible. So unboundedness is dealing with the objective function which is increasing infinitely. Unboundedness is dealing with that objective function increasing infinitely, whereas infeasibility is dealing with the constraint, not objective, the constraint, which is not satisfied, which is not feasible. Does that make sense?
Yes, sir. Yeah, thank you.
Of course, some of these things will be a little bit difficult for you until you take your time. So the key point is always note, you have to just note, one is dealing with objective function, one is dealing with the constraint not being satisfied, okay? And then we talk about multiple optimal solution. That one, you are going to get multiple solutions. That one is where the constraint is seated on the, the isoprofit is seated on the line, on the constraint line. So that one, there are multiple solutions, and you can see them. You can see the multiple solutions. But remember, that is different from unboundedness. Unboundedness, you can't see because they are infinite. They are just invisibly infinite. But with a multiple optimal solution, you can see, you will know the limitation because you know the line is going to sit. Remember the x, y axis, they are bounded. Okay, at below. If you look at the x1 and the x2, you know their limiting point, vertical limiting x2, horizontal limiting x1. So anything, any line that draws and then cuts them, we know that that's a limit. So if an isoprofit goes to sit on any one of them, we should be able to dictate that. Multiple optimal solution. As for redundancy, it's very easy. It's also has to do with a constraint. See, one of the things you will notice here is that the multiple optimal solution deals with the z value, the objective function, and the unboundedness deals with that. Because again, those two are dealing more with the z value. That's why they keep increasing. They are talking about z values becoming many. So they deal with the objective functions. Whereas the redundancy and infeasibility deal with the constraints. I think when you pick it up from that angle, you'll be able to get the idea. Any other question? I know you are all satisfied.